Hi, my name is Ho Chang Lee. I'll start off the Team 4 progress presentation. My partners are Sung Kang and Yejun Yang. Our presentation will contain the following material: a brief introduction to our paper, followed by our improvement approaches. Then we will share our progress and challenges so far. We chose to base our project on a paper titled Learning-Based Fingertip Force Estimation for Soft Wearable Hand Robot with Tendon Sheath Mechanism. It was to be presented at ICRA this year. We chose this paper because it discusses an interesting system that combines hardware and software, which made it a natural fit to apply what we have been learning in this class so far. This type of robot assists people with loss of hand mobility to grasp objects and perform activities of daily living. For the wearable hand robot to be used in daily life, it is important that the robot generates proper amount of force in accordance with the objects. For instance, when a person attempts to hold a basketball, an object that's larger than the hand, he does not overcompensate by applying maximum possible force. Also, the overcompensation would be inapplicable when holding brittle or fragile objects such as a paper cup or a delicate pastry. Therefore, it is essential that the robot can obtain fingertip information when exerting forces to the target object. The wearable hand robot has three major components: the glove, actuator, and the tendon sheath mechanism that transfers power from the actuator to the glove. It is notable that the glove is completely sensor-free, such that it reduces the size of the glove and avoids the cumbersome task of individual calibration. More significantly, the lack of electronic components in the glove mitigates the safety issues when performing aqueous daily activities such as washing dishes and brushing teeth. A learning-based approach is proposed to estimate the fingertip force of the soft wearable hand robot. Instead of attaching additional sensors to the glove, data measured from the actuation system is utilized. These include motor encoders, flexion wire tension, and sheath bending angle. To account for the nonlinearity of the robot system and sequential nature of the data, LSTM was chosen as the basis for a learning model. This model was further modified to deal with the effects of changing sheath angles by adding the bending time gradient terms. Data collected during the experiment were organized into 8 different states and fed into the LSTM model for training. The performance of 3 different types of LSTM algorithm were compared for objects of varying sizes. It can be easily seen that for all sizes, the proposed bending time gradient plus LSTM outperforms the model that does not consider the bending angle. It is notable that in the current hardware setup, the change of sheath bending angle is a significant factor in determining the output fingertip force. In conclusion, the LSTM-based model trained on data from the actuation system could accurately estimate the fingertip force without compromising the user's range of motion. We propose 2 types of improvements to the current paper. First one is making a light and portable actuation system for the wearable glove. Currently, we have access to a glove that was used in the paper, but the actuation system is unavailable. To carry out further experiments, we decided to develop our own actuation system that can be worn on the user's arm. Second one is increasing the grasping stability through slip detection function. Stable grasping can be defined as applying proper amount of force in accordance with the objects. This allows for grasping objects of various shapes, size, and hardness without the objects being crushed or completely slipping from the hand. According to Nature Review, people achieve this by applying grasping force that is 10 to 40% larger than that required to prevent slipping. Therefore, as a first step to achieve grasping stability, we plan to add the slip detection to the original model.
First of all, we are making the deep learning model based on the paper. Mainly, we use PyTorch and CUDA to reproduce the result. The reconstructed LSTM model used most common hyperparameters as same as suggested in the paper. More specifically, our model has 3 128-dimension LSTM layers topped with a fully connected layer. We use Adam Optimizer to train the model. Other training-related hyperparameters like learning rate, decay rate, batch size are also same as the paper. Simply put, our LSTM model takes a sequence of 8-dimension vector as input. Like ordinary LSTM, the output is a sequence of contact force values. This graph is the first round result of our reconstructed LSTM model. Yellow and blue line represent true value and estimate one from our model. While the model follows the general trend of grasping and releasing, the RMSE and MAE values are 4 to 5 times bigger than the paper's ones. After analyzing these results, we spotted some big points that our model missed. We will discuss about the points in next slides. Since the paper does not present enough information about the model, we had to fill out some details about the structure. For example, the paper does not present down-to-earth process of training like batching or pre-processing of the data. Therefore, we conducted several iterations of tweaking the training method. However, there is still a long way to go. We expect next possible approach can be adopting some deep learning techniques like global or value layers. Additionally, we should fine-tune hyperparameters to optimize model accuracy according to the modified structure. Also, we are planning to include gradient or bending time gradient into our model. As the paper claims, we expect accuracy improvement through using gradient bending time gradient as input. We try to make the model, but in our current implementation, PT term goes to NAN during training. We believe that one of the reasons is that when the gradient x7 is negative, PT cannot be calculated because the power term. So PT term becomes NAN. There are difficulties in finding and correcting other causes as well.
In order to build a portable actuation system, various mechanism components are purchased. Among these parts, the major components for actuation are shown on the left. Also, further assembly and testing must be performed. The motors also seem to react fast enough to adequately control the motions of grasping and releasing. The parts needed for assembly of the actuation system are shown on the right. Gearbox mechanism that can enable better control of the tendons. These parts are designed using CAD tools and 3D printed. It must be noted that the parts are not the final design and most likely be further modified. There are many challenges associated with building a portable actuation system. Some of the common ones are malfunctioning of the 3D printer or printed parts breaking during fitting. However, the most challenging task at the moment is controlling the motion of the wire. Here, it can be shown that wrapping a wire around the spool connected to the motor is almost impossible. This is caused by the lack of the tension when the wire is initially being wrapped. So we need a mechanism that can maintain tension in the wire where it is being wrapped around the spool. Here, the motor has two feeders that are tightly placed to hold the wire and provide the tension needed for wrapping around the spool. However, the feeder must be connected to the motor using gear to enable both flexion and extension mechanism of the wearable robot. To achieve this, overall lengthening of the shaft is required, and this may cause the structure to be brittle and dimensions to be too large to be attached to an arm. Careful design choices are being considered to overcome some of these issues and will be updated in the final report. Here is a crude schematic of what we hope the final actuation system will be resembled. The base plate will be located on top and bottom of the arm with motors and load cell attached to them. This type of design should enable successful grasping and releasing by flexing and extending the tendons and measuring the tensions in the wire for estimating the fingertip force. The slip detection model will be built upon the LSTM model. It will not contain the BT gradient terms since our portable actuation system will minimize the effect of since bending. When a grasped object is slipped from the wearable hand robot, we believe that the measured fingertip force will exhibit a unique pattern. So a deep learning model could be trained using the transient fingertip force data to detect the slip occurrences. Based on this insight, we plan to modify the LSTM model proposed in the paper and update the internal implementations. The improved model would not only estimate the fingertip force, but detect the moment a slip occurs. We expect the final product to resemble this figure. And this is our plan for your information. Thank you for listening.